Hello everyone and welcome to our calculus notes for section 6.2. Today we're talking about volume and specifically the disk method. So to start our conversation today, we want to talk about something called solids of revolution. And calculus is pretty amazing because it can help us find volumes of solids you didn't learn about in geometry. So take this coffee cup for example. So you can see that by keeping his fingers here in a straight line, okay, but revolving the clay around on this table, he was actually able to create a physical solid, and that's what we're talking about when we mean solids of revolution. So by rotating a plane region as bounded by a set of functions around a line, which would be an axis of revolution, you create a solid of revolution. So I'm going to click the link below for an illustration, and if you're on a computer, you can also do this and try it out for yourself. Okay, so here we have a function right on top. It's kind of curved, and then we have another function on the bottom. And in our last lesson, we learned how to find the area between these two curves. Now what we're going to do is we're going to rotate this region around the line y equals -1. You can see that here in red. And this is our three-dimensional model that we can see. And if we take this region and we rotate it, you can see that we are indeed creating a solid. So if we rotate this all the way around 360 degrees, then we would get this solid right here. Okay, so what we're going to be dealing with today is trying to find the volume of this solid right here based on this region. Now, one way to find the volume of a rotational solid is by slicing the solid into disks, which are also cylinders, of increasingly smaller widths and adding up their volumes. Okay, so we'll take a look at the demonstration here. Okay, so here we are looking at the function the square root of x, and you can see if we rotated this around the x-axis, we would get this solid right here. Okay, and what the disk method is going to do is, as we increase the number of disks, okay, so we could fit maybe one disk in here by cutting this into two regions. This disk would be nothing, and then this disk would be a little bit bigger. This would give us an approximation. So you can see our true volume is 25.1327, and the approximation here, because we can find the volume of a disk using geometrical formula, is 12.566. Now if we increase this, now we have three disks. The first disk is 0, and we get a very crude approximation again as well. But if we increase the number of regions, okay, and shrink this interval, or the height of these cylinders, you can see that the approximation is going to get closer and closer to the actual value of the volume. And this is really what we've been doing all along in calculus. So you can see here, lots of disks, our approximation is getting very closer. And if we increase this all the way up to 30 disks, you can see that our solid looks very much the same. You can see just these little steps right here, and our approximation's getting even closer. So I just want to play this for you so you can view the approximations happening. Okay, so what we're going to be doing today is learning how to make these disks, make their heights shrink to 0 and increase the number of disks to infinity, and then we're going to get a pretty good approximation for our volume. And the way we're going to do that is by using integration. Okay, so we can use the volume of a disk, which is pi r squared times the width or the height of the disk, to find the volume of each cross-section and express the volume of the entire solid in terms of a definite integral. So let's take a look at this link to see how we're going to do this. Okay, so here you can see our function, and then you can see the solid that's generated by revolving this around the x-axis. Okay, and we're going from our interval from A to B, and here you can see there's one disk here at a value of x. And you can see that I can slide that x to kind of wherever it goes. And the cross section at x is going to be in the shape of a circle. And you can see that the circle is going to have a radius right here. And that radius is actually going to be f of x, or the height of the function at that given x. So you can see that the radius is going to change based on what x is. So the radius is always going to be f of x. Now if we wanted to find the area of this circle, remember area is pi times radius squared, and our radius is now f of x. So the area of this circle is going to be pi f of x squared. And you can see the cross sections here. Now if we wanted to find volume, okay, the volume of the solid now is going to be the sum of all of these little disks from A to B. And remember, our definite integral is basically finding that sum. So it's the area of the circle, which is pi times the radius squared, or pi f of x squared, times the height of the circle, which we're going to let equal to dx, which remember goes down to 0. So all in all, the volume of the solid is going to be the definite integral from A to B of pi times f of x squared dx. So here we can see these equations set up for finding our disk method. Now when we actually apply the disk method, it's going to matter where the axis of revolution is. So in this example, we have a horizontal axis of revolution. And you can see that here marked by the arrow. So what we're going to do is take this region and revolve it around this axis. And what you want to do is take a representative rectangle here that is perpendicular to the axis of revolution. Now when you do this, the height of that rectangle is going to be r of x, and it's going to be a function of x right there. And when this happens, our limits of integration from a to b are also going to be x values. So you get x values here, and this delta x, the width of the rectangle, is going to be dx. So you can see horizontal axis of rotation, everything is in terms of x. Okay, so it says find the volume of the solid form by revolving the region bounded by the functions around the given line. So here we have f of x equals the square root of sine of x on the interval from 0 to pi, and we want to revolve this about the x-axis. So here's our x-axis, and we want to revolve it around this axis here. Okay, so this is going to get mirrored on the other side, and then it revolves right here. Okay, we almost have like a little football type of shape, and we want to draw in our representative rectangle. Okay, and the width here is going to be delta x, and then the height of that rectangle is going to be r of x. So we do have the radius is going to be in terms of x, and the width will be delta x. So here the volume is going to be pi times the definite integral from 0 to pi of the radius, which in this case is just r of x, so it's going to be the square root of sine x squared with respect to x. Okay, so that is our disk method there. And you could type this straight into your calculator, or we can clean it up a little bit. And And you can see here sine x, the square root of sine x squared is just going to be sine x. And when you type this in your calculator, we're going to get approximately 6.283. Again, we could find this by hand, but go ahead and use your calculator to get our approximation. Now in calculus it's very strange because these are really cubic units, but for some reason the textbook doesn't stress putting that there, but just realize that this is a volume of revolving this region right here around an axis. Now in our next example, we're going to be rotating a region about a line that is not the x-axis. And so it forces us just to think about our radius a little bit more carefully. So first we have the function 2 minus x squared, and g of x equals 1. Okay, so here is g of x equals 1. And it turns out 2 minus x squared, if I plug negative 1 in there, negative 1 squared is 1, 2 minus 1 is 1, so I get this point here. If I plug in 0, then I would get 2, and if I plug in positive 1, I also get 1. And so we kind of get this shape, little parabola right there. And now we're revolving this about the line y equals 1. Okay, which is right here. So I'm just going to draw that little revolution symbol there. And so this is going to get mirrored in the other side. And so this is going to get mirrored in the other side. And then rotated around. So we'll make this look a little three-dimensional. And so you can see here, we are going to have vertical rectangles, because we're revolving around that horizontal line. And the width of the rectangle is going to be dx. And now we need to find the radius of the rectangle, which is rx. Now in this case, rx is not the same thing as f of x, because f of x, remember, would be the entire height from the x-axis up. So there is your f of x. But we don't want the whole thing, we just want this part. And so we have to think we're actually going to be subtracting this amount, which is actually g of x. So r of x, in this case, the radius, is going to be f of x minus g of x. Now I don't want you to feel like this is something completely new. What if we drew the region that we were rotating? Okay, so if we were trying to find the area of this region, we would have subtracted, well, we would have gone f of x minus g of x to get that area. So the same thing happens when we're trying to find that radius as well. So let's go ahead and find r of x here. So it is going to be f of x minus g of x. So f of x is 2 minus x squared. And then g of x is 1, so minus 1. And this is going to turn out to be 1 minus x squared. So here is our r of x. And now we can go ahead and find our volume. So volume is going to be pi r squared times height, so pi, and then the definite integral. Well, where are we going to go from here? Looks like we're going from negative 1 up to 1. Okay, of r of x, which is 1 minus x squared. And then we square it, because that's part of our formula. And then dx. Alright, and then our approximation here is going to be about 3.351 cubic units. Alright, so the biggest thing here is draw what you're trying to get, draw your representative rectangle, identify the width and the radius. And you might have to be creative in finding the radius, by subtracting some functions there.